So our first speaker in here is Mike Thompson from the OpenHW Group. He is Director of Engineering Verification Task Group. Mike is a functional verification engineer and manager who's been involved in all aspects of the discipline: simulation, emulation, prototyping, and formal verification. He is a strong proponent of coverage-driven processes in the pursuit of first-time right silicon. Okay, and the title of his talk, he's going to speak for 20 minutes. All three speakers are 20 minutes in here. Accelerate your adoption of RISC-V with CORE-V verification, or CORE-V verification.
Yeah, thanks, Mike, and thanks to all of you for coming to Verification Futures. It's a great opportunity to be here. This is going to be a little bit of a different talk. I'm not so much talking about new and novel methodologies. I'm talking about applying methodologies that you're familiar with to open source design. I've got three objectives for my talk today. The first thing is I want to introduce the OpenHW Group. Not everybody on Earth has heard of the OpenHW Group. I want to introduce CORE-V. CORE-V is our branding for our family of open source RISC-V IP. This is written in System Verilog. It's permissively licensed, so you're free to use it in whatever commercial application you like. And we apply quantitative verification metrics to this IP. Three takeaways. If you remember nothing about this presentation after today, please remember these three things. The OpenHW Group applies industry-grade practices to open source designs to produce industrial-grade IP. CORE-V-VERIF is our open source System Verilog UVM environment for that. And CORE-V-VERIF can be used in multiple ways. You can use it as is. You can clone it, make some modifications, or you can just use it as a library of very cool little verification components. A little bit about the OpenHW Group. We're a not-for-profit global organization. People ask me, how in the heck do you make money selling open source IP? Well, we don't sell open source IP, and we don't make any money. We are very serious about that not-for-profit thing. We are a global organization. We literally have members from every continent on Earth except for Antarctica. No, I'm not advocating for a member from Antarctica. Don't necessarily want to go there. Our primary focus is the CORE-V family of open source RISC-V processors. So we don't build complete systems. We're focused on the cores. We do have some additional IP, peripheral IP around the processors, but primarily we're focused on the processors. I work for the OpenHW Group. So of course, I think that open source IP is great and everybody should exploit it, but that's not the case. If you're going to get involved using or developing open source IP, you really need to think a little bit about it because there's some implications. So the question is open source IP for you? The permissive license allows you to innovate. So you have the freedom to innovate when you're using open source permissive IP. However, it doesn't give you a free lunch. You're still going to have to do the same hard work that you would have to do if you're using anybody's IP. So there's money to be spent if you're using open source IP, just as there's money to be spent if you're using closed source IP. The distinction is with the open source, you can innovate. You can use it as is. You can modify it to suit your own purposes. You can use it as a way to develop, expand your capability. But don't think that all of a sudden ASICs are going to be free because you're using open source. There are three types of organizations that really benefit from using CORE-V IP, really benefit from membership in the OpenHW Group. The first one is people or organizations that don't view the processor as their key differentiator for their business. They're using the processor to do some work, but their key differentiator is someplace else. Using open source is a good fit for that. They're positioned to take advantage of the potential cost savings from using open source IP. Not everybody is, but a large number of companies are. And we get a lot of we have at least a third of our members are members that want to have access to the ecosystem to develop their own capability or to demonstrate their capabilities. Speaking of members, we got a lot. We're a different kind of an open source company. First of all, we're an open source company. There's an awful lot of organizations that just push open source IP out into the ecosystem, publish it on GitHub or wherever, and they don't actively support it. We actively support it. We use industrial processes to create industrial grade IP. That's the mantra. You'll hear me say this 100 times. When it comes to verification, I'm the verification guy, so this is what I focus on, the thing in red. We use quantitative verification metrics on our open source IP. This makes us not completely unique in the open source space, but rather unique in the open source space. There are other organizations that are sort of getting in, starting to do this as well. But really, this makes us stand out. Another thing about the Open Hardware Group is we have a lot of members, but you only get out of CORE-V what you put into it. A drive-by shooting, just coming in, taking the IP, putting it in your chip, probably you're not going to get maximum benefit out of that. So how does this work? I get this a lot. How does it work? Because the Open Hardware Group does not have an army of verification engineers. The army of verification engineers comes from our members. So how do we work together? How does that actually work? This is my attempt to illustrate this in one slide. The center of our universe is the repository. All of our code is hosted on GitHub. These are public repositories. You can go look at it right now. We've got 7 different cores, 7 different repositories, plus other repositories for things like verification, software development. There's lots of people on that slide. Not one of those people needs to be an Open Hardware staff member. In fact, some of our projects, there is very little activity, very little direct support from Open Hardware staff. It's all driven by staff that are employed by our members. So it works sort of like this. There's a group of people that are called the committers. They're basically the people that maintain the code base. They will assign tasks. Maybe a task is to, write some coverage. Maybe a task is to fix a bug. Whatever it is, develop a UVM agent. Whatever that is, that gets assigned to a contributor. Both committers and contributors are using their own compute with their own tools on their own premises. When they're done their task, they will submit the code to GitHub using something called a pull request for those who aren't familiar with GitHub. So they issue a pull request. This triggers off 2 things. An automatic CI will launch. This automatic CI, I've shown it running on AWS. This is a facility that the Open Hardware Group maintains. Not all of our cores are run on that. Some of our regressions are run on premise from some of our members. But anyway, wherever it's run, the CI is kicked off, and the committers will get a notification that something needs to be looked at. If it passes CI, if it passes the review by the human committer, it gets merged in, and now it's part of the code base in GitHub, and the cycle just continues until we get done. I'll talk about done in a bit. I said earlier that I'm a real quantitative kind of person. I like numbers. The coverage is 82%. 97% of our test cases are passing, those kinds of things. But when you want to promote your IP, when you want to talk to a general audience, not necessarily a verification audience, you need something that's a little bit more qualitative. And we've adopted the technical readiness level scale. This was developed by NASA in the 1960s, and it's widely used in industry, not everywhere, but it is widely used. There's a bunch of TRL levels. So TRL 0 is, I got an idea. It's going to be great. And TRL 9 is, I've been in production with this for years, and it just works. And there's a sliding scale. The open hardware technology outputs tend to go from about TRL 2 to about TRL 7-ish. But I've got TRL 5 blocked off because that's where that's our sweet spot. The idea with TRL5 is it's soft IP, so RTL, that you can go to your boss with and basically say, we can put this IP in our device and it's going to work and there won't be any production gating bugs. That's the hand-wavy description of TRL5. Open hardware adopters, so these are members that get involved with open hardware that want to use the core or the CORE-V IP. They'll play somewhere around TRL5 all the way down to TRL9. So there's the developers that are that tend to focus on TRL5 and the adopters that go to production with the IP. That's all great, but I'm the numbers guy. I want to know, how do you know it's TRL5? How do you know it's fully verified? So we have quantitative metrics for that. Our quantitative metrics will look very familiar to anybody in this room that does verification work, right? There's the sign-off checklist, right? Do you have 100% conditional code coverage? Do you have 100% line coverage, branch? Do you have functional coverage? Is it at 100%? Did you do all the things that you needed to do to sign off your documentation, your IP licensing, your RTL design, simulation, verification, formal verification, software requirements? It's a large set of checklists. These are all open source artifacts. They're all published on GitHub. You can go have a look at them today and determine for yourself whether that is sufficient for you to use this IP in your designs. If it's not, please call me because I want to hear what else we should be doing to make you happy. So I haven't talked about the verification environment yet, so I'm going to start doing that. What is CORE-V-VERIF? Well, it's a GitHub repository at the end of the day. It is the verification environment for the CORE-V RISC, the CORE-V cores. You can use it in one of three ways. You can use it direct, would you basically use it as is, where is, put your core into the environment and off you go. You can use it indirectly, where you clone it into your repository and make repository specific modifications. And then there's just using the library. There's a large number of reusable components in there, UVM agents, functional coverage. You can just reuse those as components from a library if you choose to. I'm not going to go into this in too great detail. I'm going to point out a couple of things though. So this is the CORE-V-VERIF implementation in a picture. The big pink box on your right-hand side, that is a straight up plain vanilla UVM verification environment, right? It should be recognizable to everybody. The RTL is in white in the middle, and it sits in a test bench. This is where we bind in the SVA. This is where we bind in our tracer. The tracer produces a trace record that is scoreboarded against a reference model. The whole thing is driven by a bunch of UVM agents. The UVM agents are driven by a bunch of virtual sequences. And that is the environment. And you can use that verbatim. There are a couple of additional things. On the far left-hand side is the instruction generator. This is the CHIPS Alliance RISC-V DV. We've been using this extensively for years. It's pretty good, not great, sufficient for what we do. I'll put it that way. That produces a RISC-V constrained random, pseudo-random test program that has to run through a tool chain to produce the machine code. The machine code is executed on the reference model and on the core at the same time. As each instruction is retired, the scoreboard checks the architectural state of the core and of the reference model. If they're not the same, that's an error. You get enough errors and the test case fails. On top of all that is a YAML description that keeps the generator, the tool chain, and the UVM environment all consistent. You have to have a common memory model, for example, to make this run. Some important points. Everything represented on that picture is a free and open source artifact, except for the reference model. That's the one exception. We've got two models for the reference model. One is a commercial option from Synopsys called ImParis DV. I believe it's still called ImParis DV. That is by far the most popular reference model used in CORE-V-VERIF. Most projects use it. There is an open source option available as well. 2 cores are using this, and this is a reference model based on Spike. Spike is a instruction set simulator from RISC-V International. So I'll talk about the usage models very quickly. The direct model is the one that most organizations that use CORE-V-VERIF adopt. Basically, thank you. Basically, you add a directory to CORE-V-VERIF that represents your core. You put the core-specific stuff in there, and then you're off to the races and you're running it. The pros are for using this is basically you get 80% of the work done for 20% of the effort. The cons is that remaining 20% is a lot of work. This is the idea of direct use of CORE-V-VERIF in a picture. Everything with a star represents something that you would modify in your core-specific directory. So of course, the core and the test bench that instantiates the core is core-specific. Virtual sequences, those will be core-specific. The configuration for the test bench generator, the configuration for the reference model, by definition, those will be core-specific. The infrastructure is all there, and anything that you don't have to modify, you can just use as is. Indirect use is basically, we've got one core, it's called the CVA6, that uses this, and what they do is they actually bring in CORE-V-VERIF into the CVA6 repository and make local modifications there. Personally, I'm not a real fan of this because it makes it hard to take advantage of any updates to CORE-V-VERIF that may be useful to you. But this is currently being used by the CVA6. The indirect use is just to, take a look at all the verification components there and say, boy, I could use those. This is some good verification IP that I can leverage. Okay, so just to wrap up, remember, there's a few things I want you to remember. CORE-V is the family of permissively licensed open source RISC-V cores curated by the OpenHW Group. CORE-V IP is industrial grade. CORE-V-VERIF is our UVM environment, and there's no free lunch. That's an important thing. With that, I'll take any questions if there are any.
Any questions from the audience? Okay, perfect. Thank you very much, Mike.
Thanks.
Okay, hi. Yeah. Just to say as well, we use this ourselves at the test of, and it does work out the box, by the way. It does work straight out of the box, and you can plug in any open source RISC-V that you want as well. So we're big users.